Okay, as we reach the conclusion of guide sheet number 3, we want to look at what angles are best if you're trying to get maximum range. Again, the range is really actually based on the velocity in the horizontal, but if you change the angle, you're going to change the time spent in the air. So there is a best angle for launching to get maximum range. For each of the three angles, 40 degrees, 45, and 50, I've calculated the y and the ux. Notice that they switch positions. So the sine of 50 is the same as the cosine of 40. So they're really just switching locations. If I want to find the distance in the x, I'm going to take the velocity in the x multiplied by the time that it takes to make the total flight. Now, the time it takes to make the total flight is actually 2 times the time to the top, which is uy divided by g. So if I'm actually calculating the distance in the x, it's how fast I'm going in the x, multiplied by 2, multiplied by how fast I'm going in the y, and we're going to divide that whole thing by g. Again, uy over g times 2 is the time total, multiply that by ux. Now, in the case of 40 degrees, it's going to be 30.6 times 25.7 times 2 divided by g, and you're going to get a total of 161 meters at 40 degrees. At 50 degrees, it's going to be just in reverse, but since you're multiplying, it doesn't matter. It'll be 25.7 times 2 times 30.6, and you'll also get 161 meters at 50 degrees. But when you go for the 45, it'll be 28.3 times 2 times 28.3. And then divide that by g, that's a larger number. That's 163 meters at the 45 degrees. So if you're looking to hit or get the maximum range in the absence of air resistance, it's going to automatically be you want to hit the object or launch the object at an angle of 45 degrees. You're maximizing two things there. You're maximizing the horizontal velocity. Okay, if you shoot it higher, you'll spend more time in the air, but you're not going that fast in the x direction. If you shoot it with a shallower slope, you're going to be going pretty fast in the x direction, but you're not going to spend much time in the air. It's that midway point, 45 degrees, where you maximize the time you spend in the air and the horizontal velocity. If we compare the peaks, keep in mind if we're launching at a lower angle, the trajectory is going to be, we can call it flatter. 45 degrees would be the maximum range, and then 50 degrees would be a more, and these are exaggerated, a steeper launch, more up than over. To determine the SY, it's equal to uy over 2 times time to the top, or time up, as we saw before. And so that's time to get to the top is uy divided by g. So what we really have here is uy squared over 2g. So if we put in the values for the vertical velocities at the beginning, for 40 degrees, we're going to get a maximum peak of 33.7 meters. At 45 degrees, we'll get a maximum peak of 40.8 meters. And then at 50 degrees, we'll get a maximum peak of 47.8 meters. So shallow, not very high arc. In the middle range arc, 45 degrees. Then when we go beyond 50 degrees, we have a pretty steep arc, so we have a much taller SY. So shorter SY here, middle SY at 45 degrees, it's the middle of the angles, and then SY when you launch it greater than 45 degrees, definitely higher than it is over. Now, one more thing that goes with all of this, and we'll go to one of the simulations from the people at FED. What's the impact of air resistance? So far, everything we've said has been without air resistance. So if I take a pumpkin and I launch at an angle of 60 degrees at 15 meters per second, I'll get this arc. Now that's going to be, in the absence of air resistance, a perfect parabola. It's It's going to be perfectly symmetrical. I can calculate the range. I can do everything we've just been doing. But what if there's air resistance? So I'll click the air resistance button on. I'll put a drag coefficient of 0.6 for the pumpkin. It's a round, it has a fair amount of drag. And I'll fire at this point. Now you should notice two effects. One, the range is shorter. Some of the energy of the shot has been expended in moving the air out of the way. There's been this acceleration against your motion because of the air resistance. Also, you should notice it doesn't reach the same peak height. Okay, so it loses both height and range. On the way up, there's an air resistance that's downward, so that causes you not to climb as high. On the way to the right, the whole time to the right, we're actually going to be losing some velocity because we'll have some acceleration against us. Now, because air resistance changes as velocity, that's a fairly complex calculation. So at this point in your career, we wouldn't expect you to be able to figure out the effects of air resistance other than if you look at the objectives qualitatively, the idea that it's going to reduce both your maximum range and your maximum height. That's going to be your impact. If you just wanted to see, we could change the drag coefficient to an even higher value and then fire, and you'll see that it has even greater impact. So more drag, more acceleration against you, less range, less height. Okay, so that's it for projectiles at ordinary angles. We'll need to look at some irregular launches. What if we're on a height and then we throw it up at an angle? How do we deal with that? And that'll wrap up our study of projectiles.